In this video, we begin section 3.3, which is on the number of solutions of a linear system. The goal of this section is to develop methods of determining the number of solutions of a linear system by analyzing the augmented matrix of the system in row echelon form. In the previous section, we saw that a linear system has either one solution, no solution, or infinitely many solutions. In chapter 5, we will prove that these are the only three possibilities. Recall that when solving a system using Gaussian elimination, we reduce the corresponding augmented matrix to REF, row echelon form. In this section, we will determine the number of solutions of linear systems by examining REFs of their corresponding augmented matrices. That is, we will determine the number of solutions of linear systems without fully solving them. Now, since performing elementary row operations on an augmented matrix does not change the solution set of the corresponding linear system, we can focus our study on augmented matrices in REF. Note that since an augmented matrix in our REF is also in REF, the following discussion applies to augmented matrices in our REF as well. We first define the rank of a matrix in definition 3.3.1. The rank of a matrix A is the number of leading entries it has in one of its row echelon forms. We denote this number by rank of A. Let's look at example 3.3.1. We want to find the rank of the following matrices. In part A, we have an augmented matrix. What is the rank of this augmented matrix? The rank of a matrix is the number of leading entries it has in one of its row echelon forms. This matrix is already in row echelon form, and so we simply count the number of leading entries in this matrix. 1, 2, and so the rank of this augmented matrix is 2. In part B, what's the rank of this augmented matrix? Again, this matrix is already in row echelon form, and so we count the number of leading entries. There are 3 leading entries, and so the rank is 3. In part C, what's the rank of matrix C? Well, again, this matrix is already in row echelon form, and so we count the number of leading entries it has. It has 3 leading entries, and so the rank of C is equal to 3. In part D, we notice that this matrix is not in row echelon form. In order to find the rank of this matrix D, we first need to find a row echelon form of D. And so we perform elementary row operations. We will use row 2 minus 2 row 1 and row 3 minus 3 row 1. So the first row stays the same, 1 minus 1, 2. The second row becomes 2 minus 2 times 1, that's 0. 3 minus 2 times minus 1, that's 3 plus 2, which is 5. Minus 2 times 2, that's minus 2 minus 4, that's minus 6. And the third row becomes 3 minus 3 times 1, that's 0. 2 minus 3 times minus 1, that's 2 plus 3, which is 5. And 0 minus 3 times 2, that's minus 6. So this matrix is not yet in row echelon form, but almost. We can perform the row operation row 3 minus row 2. first row stays the same, 1, minus 1, 2. Second row stays the same, 0, 5, minus 6. And the third row is a row of zeros. This matrix is in row echelon form. And so now we can find the rank of matrix D by counting the number of leading entries in a row echelon form of matrix D. There are 2 leading entries, and so the rank of D is equal to 2. Now, A aug and B aug in example 3.3.1 are augmented matrices in row echelon form. We would like to determine the number of solutions of the linear systems they correspond to, without actually solving these systems. We will see that the rank of these augmented matrices will help us do just that.